everybody. In the Programming Language Concepts course, in today's lecture, we're going to cover chapter number 7. Chapter 7 is on expressions, assignment, and assignment statements. And the lecture itself can be found in the 6, 7, and 8 PowerPoint. So it's chapter 6, 7, and 8 in the lectures folder of the class website. So please go over there and make sure you've got this file downloaded and follow along with me as I go through it in this video. So chapter 7 starts on page 49. So the 3 chapters are in the same PowerPoint and it starts on page 49. So let's begin with chapter 7. So arithmetic expressions, overloaded operators, and this will probably end up being a 2-part lecture, by the way, as well. Type conversions, relational and Boolean expressions, probably going to get through type conversions and relational Boolean expressions in this video, and then cover short circuit evaluation, assignment expressions, and mixed mode assignments in the next video. So it won't make this video too long, make it about an hour or so. So arithmetic expressions. Okay, so if you're going to write your own programming language, and remember we're taking off our programmer's hat and we're sticking on our language designer hat. So you're interested in creating your own programming language, and in this programming language you have to invent this concept, and the concept that you're inventing is this arithmetic expression. Okay, so most people would say, oh, aren't we just going to follow math rules? You know, why don't we just have the arithmetic expressions follow basic math rules? And you know, most programming languages actually do. There are some variations though. So we've learned that variables are abstractions of memory cells, and that the abstraction of the computation takes place with the CPU, and that we have operations that might take place with an arithmetic logic unit, an ALU, and arithmetic and logical expressions that might exist in languages to perform operations. Now, are the operations going to be performed exactly how they're performed mathematically? Probably not, because we have to take into consideration this abstraction from a programming language concepts perspective. It's not like we are working with the true concept. We have an abstraction of the concept that we have in the language. So their evaluation was one of the motivations for the development of the first programming language. Actually, but you know, in the beginning of time, the computer itself was nothing more than an elaborate calculator, and that computers were meant to do calculations. And so the first programming languages that are out there, especially in the beginning of time, they were math languages, precisely. So, and then we added on other features to those languages. So arithmetic expressions, they consist of operators, operands, parentheses, and function calls. You could have arithmetic expressions that are performed in functions. So here are some design issues for arithmetic expressions. Now remembering these issues are not negative things, they're positive. Well, it could be negative and positive, but there's no connotation of the word issue being a negative word. In fact, you can substitute the word issue with design considerations or design features. So if we want to work with arithmetic expressions, and the first one here says, what are the operator precedence rules? And you might notice number 2, what are the operator associativity rules? And if you think about the midterm and what we learned about ambiguous grammars, those are the 2 things that make a grammar ambiguous, is the lack of operator precedence rules and the lack of operator associativity rules. If you don't put those rules in the grammar, you leave them out completely, you have an ambiguous grammar, because the parsing mechanism needs to figure out what these rules are and apply some arbitrary rules. But when you think about designing arithmetic expressions, somebody has to come up with these rules. How many levels of precedence, and how many, what order do we want to do the operations in? It's a difficult consideration. We're going to show you some examples in a few minutes of how it actually differs in different programming languages. But yeah, you have to decide on these rules that you're going to put in your grammar in order to support the arithmetic expressions. Also, the order of the operand evaluation. There's many choices that you have with the order. Am I going to do the first one first, the second one second? I mean, for example, the parameters that get sent to functions, is there going to be a particular order to them? And if I'm going to use them in a calculation, do I substitute a function call in first before I evaluate the variable? And there's different complications with the abstraction. And number 4, are there restrictions on the operand evaluation side effects? What if we get a fraction instead of a whole number out of a calculation? Is it going to automatically round something? And what if a call to a function changes something outside of the function, or the returns from the function call creates a side effect, and the side effect gets transferred over to the operand evaluation? And what are we going to do with that case? And then number 5, does the language allow user-defined operator overloading? C and C++ are like the last languages out there that support operator overloading, by the way. Java, there's no operator overloading capabilities, and you really can't do it very much in Python. You can do a little bit of overloading in Python from an object-oriented perspective, but not operator overloading. To overload an operator, we know changes the behavior of the operator, but you could overload like the plus, turn it into a minus, and the minus turn it into a plus, and then someone who's reading your code is gonna look at that and go, wait a minute, how come it's adding when we're using a minus? And what's going on with this? So you can cause some confusion. So there's some pros and cons to allowing operator overloading. The reason why C and C++ actually allow operator overloading is because how are you going to change the behavior to add 2 points together in object orientation? For example, you have a point with an xy and another point with an xy, and you want to know the distance between the 2 points, or you want subtraction, or you wanted to add them together, you wanted to do something. You can't really do it unless you overload the operator. So overloading operators in C++ was a means to make objects behave correctly. And if you took the C++ class, then you know that in order to print something to the screen, you want to print the object to the screen, you have to overload the cin and the cout, or the cout operator. Actually, not the cin. You have to overload cout in order to print the object information to the screen. Otherwise, what you're going to print is the memory address of the object. That doesn't mean anything. So operator overloaded got added to C because it solved another problem. It was used as duct tape or a band-aid to solve a problem of there not being any object behaviors. Java just built it into the object and said, we're not going to overload any operators here. Also, mixed mode expressions, mode mixing, is it allowed in expressions? Like taking a float and adding it to a double, which should work, but it doesn't work in C or C++ because it's typed, and the compatibility is based on the data types, not on the variables themselves. In a language like Python, it is possible. So mixed mode expressions are possible in some languages like Python in some cases, but they're not in other languages. So when it comes to operators and the operands, the expression consists of both the operator and the operands. The operators specify the actions to be performed on the data. The data processed by the operator are called the operands. And the operators taking a single operand is called a unary operator, for example, plus A. Then we have the binary one, we got A plus B, 2 of them, or we can do 3 of them, or we can support as many as we want. In most imperative languages, and if you go back to the definition of what an imperative language is, C would be an imperative language, the binary operators are infix, which means the plus is in the middle. It's infix. And I believe the next slide has the differences with the infix, and no, it doesn't. Let me explain this then. We have infix, which means it's in the middle, prefix, which means it comes before, and postfix, which means it comes after. This is prefix. We have plus A. We can also go A++, which would be postfix, and this is infix. So those are the 3 combinations. The book has this in a little bit more detail, but those are the 3 combinations you have With the unary, you're going to have the pre or the post. You need more than one. You need more than one operator. Operand to do to do an infix notation. And the operators can come in multiples. Like you can use a plus plus, a plus equals in some languages. So you can do them in combinations as well. So operator precedence, and those operator precedence rules we looked at before the midterm there when we talked about ambiguous grammars. The definition of operator precedence rules are for expressions. The evaluation defines the order in which the adjacent operators of different precedence levels are evaluated. Adjacent means that they are separated by at least one operand. So what order are we going to do them in? That would be, what you learned in math, where you did parentheses first, unary operator second, exponentials if the language supports it, multiplication, division, and then on the last of the list, the lowest level is going to be the plus and the minus. This is language dependent. It depends on the programming language as in terms of which precedence rules and the types of precedence rules that are defined. Some languages have more levels defined than others, and some languages leave it freeform and don't put any operator precedence rules in there. When it says see the book for details, there's a couple of really good examples in the book that kind of go over the operator precedence levels. You don't have to know which language supports which operator precedence levels. In fact, most people don't know this actually. And then you don't know it until you figure out, oh, it's doing the wrong calculation. How do I get the right calculation to perform? Well, then you start playing around with parentheses, or you start playing around with stuff to see how the operator precedence rules work. So the other one there was the associativity rules. Also can be ambiguous if you leave them out. So operator associativity rules for expressions evaluate to find the order in which the adjacent operators with the same precedence level, how are they evaluated? So the typical rules usually go left to right. This would be, for example, if we were doing an assignment expression. If I said that A was equal to 1, I'm going left to right. If I go and I put like AB is equal to 1, I'm going left to right. I could go 1, 2. I can go, that would be right to left or left to right. Yeah. Most of them usually it goes left to right. APO is different. All operators are equal precedence, and all operators associate right to left instead of left to right. Usually in C, C supports both. But for the most part, a lot of them are left to right because English people, Americans read left to right. Not all languages read that way. And the associativity rules do often follow the spoken language. So if you are accustomed to going right to left, then you might do your assignments expressions right to left instead of left to right. So precedence and associativity rules can be overridden with parentheses by putting parentheses around numbers. For example, A plus B minus C minus D, you can change which ones get done first with which, with parentheses that you'd be putting around it. So the order, the process is for the operator and for the operand, not the operator, but the operand evaluation order. Usually variables are resolved first. So the process starts out with, and this is not set in stone, and it can change language by language, but this is the typical order. Variables, they're fetched first. You just fetch and you get the value from the memory cell, and you substitute that value in for the variable. I think any constant values that might exist come next. So sometimes you fetch from memory, sometimes they're constant in a machine language instruction, sometimes they're just a placeholder somewhere. Any constants would come next. And then parenthesized expressions. So you evaluate all of the operands and the operators first of the parenthesized things that you're putting in parentheses. And then we have the function references. This is the case of most interest because this is where we run into function side effects, or we run into which function are we going to run first, second, or third. And the order of the evaluation is crucial. It is because if a function comes back and changes something and we run this function first and then we run the function second the next time we do it, we change the order, we might come up with different results. So this is where languages that are called functional programming languages usually have what's called a referential transparency when it comes to the function evaluation, and so which means there's no side effects. So languages like Scheme that we looked at, the Scheme language, and Lisp actually has this as well. So it's it's functional transparency. So it doesn't matter which order you run the functions in, their evaluation order will always produce the same result regardless of the order. Languages like C, C++, Java, other imperative style languages, the order does matter because there's a potential of side effect. So functional side effects is when a function changes a parameter or a non-local variable after it's been called. And we know that we're able to do that in an imperative language like C. You can do it in Java. You can even do it in Python for that matter. And Python is not considered a functional programming language. So functional programming languages are characterized by functions that don't have side effects. And it doesn't matter what order you run those functions in. They're meant to be evaluated in any order you want to run them in. And they never cause a problem because they always produce the same results. So when it comes to that operator overloading, some is common. For example, the plus for ints and floats. You can overload an operator so it can add a mixed matched types. Probably not good practice because it creates bad readability in languages. But for the most part, you could. There might be some is potential trouble. For example, if you overloaded the asterisk in C or C++, if you do overload that asterisk, which is used for the reference and the dereference in C or C++, you're going to end up with a problem because how are you going to know what to use? And now the compiler can't do any error checking. So you have a loss of compiler error detection if you overload the asterisk. So now the asterisk is doing, let's say, multiplication or something instead of a pointer reference. And this is the shift 8, the asterisk I'm talking about. So if you introduce some new symbols into the language, and you basically can take any symbol you want, like the @ symbol or the $sign or the carrots or something, just pick one of the symbols off the keyboard that's not being used for anything else. Then you can create operations for the new symbol, and you don't have to overload operators. So overloading of operators can be avoided by introducing new symbols, either in the language itself or by the programmer. And if operator overloading is a programmer feature. C++ allows user to overload operators, any operator you want, with one exception. You can't overload the class or structure, remember, the dot, and you can't overload the scope resolution because then the entire C++ language would fall apart. So you can't overload the dot and you can't overload the scope resolution operator. Otherwise, the C++, the entire concept of the language is broken at that point if you overload those two operators. So you don't, and in Java, you can't overload any operators at all. It's just not allowed. And there's no reason, really no reason to have to overload operators. You should be able to use object features. But at the time in which C came out and C++ followed C, the true concept of the object didn't really exist. So it's, it was a makeshift band-aid to make objects work correctly. So there are some potential problems with overloading operators, even when you do them correctly. The users, you can define nonsense operations, like the plus being used for the minus being used for the plus. You can actually overload the asterisk if you want to. That one's not limited. The only two that you cannot overload are the dot and the 2 colons. But people change it to like take the semicolon that's supposed to be at the end of the line and overload it to do something else. It might not make any sense to somebody reading it. So readability may suffer. So yeah. Readability is going to suffer if you start overloading those operators. So now we have implicit type conversions. So typecasting is an interesting concept in C and C++. It's also possible to do an upcast or a downcast in Java. You can also do a typecast in Java as well. The implicit typecast is when, or type conversion, is when the compiler is doing it for the programmer. And so a narrowing conversion is generally acceptable. So a narrowing one is where you take a little number and you put it into a big memory space. So one that converts an object to a type that cannot include all of the values of the original type. Excuse me, that's a widening, is what I just explained. The narrowing is when you take a big number and you stuff it into a little space and not all of it fits. To make it narrower makes it smaller. To make it wider, you take a little number, and that's what I originally started out doing. I flipped them around. If you have a little number, the little number is going to fit into the big space because you're going to widen it. You're going to make it bigger. You're going to add more memory space to the number. That's acceptable. To take some memory away from the number is not acceptable because you're narrowing it, which means you're going to make it so not everything fits, which means you're going to lose some data. It has a tendency, narrowing conversions have a tendency to lose data. Both of them are allowed in C or C++. And usually you'll get a compiler warning that says you're narrowing, not advisable. So a narrowing conversion is one that converts an object to a type that cannot include all of the values of the original type. A widening is one in which the object is converted to a type that can include at least approximations of all of the values of the original type. That's because you're making it bigger, you're putting it into a bigger space. To do a type conversion converts the type or converts the number. So for example, I can make 12 into 12.00. But if I make 12.19 into 12, I got rid of the 19, I narrowed it, I made it smaller, I'm going to lose my precision. So a mixed mode expression is one that has operands of different types. And so you can do a conversion when you do a mixed mode expression if you're going to support it. And this is what Python does. So let's say, for example, I have the number 12.19. And let's say the other operand that I'm going to use in this mixed mode expression is the number 5. Well, I can come up with 17.19 out of that if I add them together, assuming the 5 had a 00 next to it. So I would implicitly convert the 5 to a 5.00 and add it to a 12.19 to get my 17.19 at the end. Now I'm widening, and so that would be a widening cast for a mixed mode expression. So the concept of a coercion is an implicit type conversion, and that's what I just did. I coerced the 5 into 5.00. I made it wider. That's a coercion. So I made it wider so that I could add it with another number and get the precision for the 2 decimal places, even though I had an int and I had a float or a double when I started. So disadvantages. So that's the advantage of the coercion, is to be able to make the numbers compatible so that you can do calculations with them. A disadvantage of it, they decrease in the type error detection ability of the compiler. Yes, languages like C or C++ that are supposed to be doing type checking don't allow mixed mode expressions because they want you to actually explicitly convert the 12 or the 5 or whatever, the 5 into a float. So you couldn't take a double like 12.19 and add it to an int like the number 5 in the language of C. You can do it in Python, but you can't do it in C or C++. You can't do it in Java either, without first taking the 5 and converting it to whatever data format the 12.19 was in. So if it was a float, I need to convert it to a float. If it's a double, I need to convert it to a double. And so I have to take that int, the 5 that's stored in the int variable, convert it to a double or to a float, it has to match the other one, and then add it together. So there's an explicit conversion that's done so that a widening or a narrowing doesn't have to be done. And it's not done implicitly. It's done explicitly by the compiler. And so we can't do that implicitly in C or C++ because otherwise we would have no error checking. So how are we going to be able to tell if the types are compatible if we can't tell because they have mixed mode types? So like if we wanted to do something different with it, how do we know that the calculation is actually going to work? In most languages, all numeric types are coerced in expressions using widening conversions. That's what I just explained with the Python language. So most languages, not C or C++ or Java, that require an explicit type conversion to change the type so that they match, so that type checking can be performed. And in Python, you don't have the same level of type checking. The compiler can do it implicitly, and it'll widen it. It won't narrow it, but it'll widen it. In some languages, actually some versions of Python will narrow, but it'll tell you a warning. It'll say, unsafe cast, narrowing cast, letting you know that you might have lost some data when you did this because we casted it and we lost the precision. That's like if I did an explicit cast, let's say on 12.19, and I put it into an integer, I'm just going to get 12. That would be a narrowing cast. And if I did that, the compiler would come back and hopefully tell me, hey, you just lost some data from there. You narrowed to 12.19, you stuck it in an integer value, so now you only have 12. And then my question is, what happened to the 0.19? Well, it's gone. It doesn't fit in the int variable. So yeah, it would be an unsafe cast if I needed to get that 0.19 back. I don't know if I'm going to get it back. Relational expressions. So you use a relational operator, operands of various types. Go back to discrete math. This is the ands, the ors, the nots. So you want to, let's say, evaluate to some Boolean representation. Usually when you're doing a relational expression, you're doing an evaluation that's going to come out to true or false. So is it this and this or that, this and this, but not that? You're looking for a true or a false. So generally, they don't always evaluate, but they can. For the most part, they do evaluate to some Boolean representation. And then the relational operators always have lower precedence than the arithmetic operators. So in the case here, this one's last. So this would get done, a plus 1 would be done first, or actually, if we had multiplication in there, we would have, or is that a power, 2 to the power, or 2 times b, would be, depending upon the language. Some languages actually, this would be 2 to the b. So it depends on the language that you're looking at here. Because there's no this is a generic text here. It's not necessarily related to any particular language. But what's saying is this is going to be evaluated probably first, this is going to be probably second, and this one's going to be third. So it takes on a lower precedence level. And then in the Boolean expressions, the operands are Boolean, and the result is a Boolean. So here's some examples. This should be moved over one more tab space, because this is the C, we have the and, the or, the not, Ada doesn't. Actually, Python takes over both C and Ada syntax. You can use the word and or. You could type out, OR, or not. You can use this in Python. You can also use the C syntax in Python, which is which doesn't come from anything. They decided to use symbols. The Fortran, it's case sensitive. This was case sensitive back in the day. And in Ada, also in Python, it's not case sensitive. You can put capital A and D or lower A and D in there. So C has no Boolean type. So it uses the int type for all of the false and non-zeros for true. Which is actually kind of an interesting note to say about this. When we do the relational expressions, We're looking for a 1 or for a 0 in C to come back. That's how you can do an assignment expression in a relational expression place. For example, if I were, to test if, I could say, if, and then opening parenthesis, x is larger than 5, close the parenthesis, and then, have my opening and closing brackets and put some code in there. And then if x was larger than 5, this code would run. So that would come back. If x was larger than 5, it's going to come back true. If it's true, it's going to run. So when I do an assignment expression, I can go like integer I is equal to 5. Well, that also comes back true if it works. So the return on the assignment expression comes back with a true. So that's how you can get away with that in the C language and in C++. You can put an assignment expression in there. You can say, x is equal to 5 instead of if x is equal to 5. And just do an assignment expression. You can run a function call. You can do anything that has a return value of 0 or 1. All of the assignment expressions have a return value of 0 or 1, depending upon whether or not they are successful. So as long as, if I said integer I is equal to 12.19, it's going to come back false because you can't take a float and assign it to an integer value. But if I assigned it an integer value, it would come back true. And if it came back true, then the if statement would execute. That was one of the interesting things about C that is not quite the kosher way of programming, but people like to do that all the time because it works. So as I mentioned, I'm probably going to make this into a 2-part video, and I think I'm going to stop right here actually with the relational expressions. Makes the videos a little bit easier to digest, I believe, the shorter the video. And again, just to reiterate a point, you don't need to know how relational expressions work, like the example I just told you about C. It's just for your knowledge, just so that you have some comparison with other languages. You don't need to memorize what languages support which relational operators and how the relational operators work in like every language out there or sampling of languages. You want to know what the concept of a relational expression is, and you want to know the concept of a relational object. And on a side note, C doesn't have a Boolean type, but you should know that Java does actually. Java does use it does have a true Boolean, like it has a true string as well. So I'm going to end this video, and then the next video will pick up on short circuit evaluation because I want to make this in slightly easier, more digestible chunks. So we will stop this and call it part 1, and then part 2 will continue with the next set until the end of chapter 7. So thank you for watching, and stay tuned for part 2.